Hello dear students, today we are going to discuss more about electromagnetic inductions. As a part of syllabus, we have some points about electromagnetic inductions. These are the some conditions for electromagnetic inductions. From this figure, we can see that from the figure A, the Faraday's pulled a loop of wire to the right through the magnetic field. Then a current flows in the loop. Second conditions, he moved the magnet to the left, holding the loop still. Again a current flowed in the loop. The third condition is that with both the loop and the magnet at rest, he changed the strength of the field. He used an electromagnet and varied the current in the coil. Once again current flows in the loop. These are the three conditions he tried for the magnetic inductions, the experiment side. After the experiments, what do you mean by the Faraday's law? A change in magnetic field induces an electric field E equal to minus d phi divided by dt. Previous class we have discussed about the electromagnetic inductions and the Faraday's law. If, as Faraday's found empirically, the EMF is again equal to the rate of change of flux equal to closed integral E dot dl equal to minus d phi divided by dt, then E is related to the change in B by the equations closed integral E dot dl equal to minus integral dou B divided by dou T into dot dA. This is Faraday's law. In the integral form, we can convert it into differential form by applying the Stokes theorem. Del cross E equal to minus dou B divided by dou T. This is the Faraday's equations. Next we are moving to the some of the experimental part with the some videos. You can see this is the current is flow to the coil. There is a call to him.
Oh. Oh. Huh?
After the discussion of oyster.
Oh.
This indicates presence of magnetic field. There is electric current. It is go to the coil. Also there is a deflection in the needle.
Yes.
This proves that electric current produces a magnetic field. There is a connection between electric current and magnetic field. Also, it is possible to magnetic and electric. It is not deflecting, that means motion of the magnet is causing the needle to deflect. Now let me keep the magnet fixed and move the coil. These are some experiments we have done. Oh, I can still see deflection. Current is induced in the coil due to relative motion between the magnet and the coil. Relative motion, that is important point. Also the magnet and the coil. When I move the magnet away, needle deflected in opposite direction. That means the current is now being induced in the opposite direction. Now let me try to reverse the poles of the magnet. Oh, the deflection reversed when the poles was reversed. North pole going inside the coil, deflection towards the right. North pole coming out of the coil, deflection towards the left. South pole going inside the coil, deflection towards the left. South pole coming out of the coil, deflection towards the right. Let me try to move the magnet faster motion of magnet, faster needle deflection, faster motion, faster needle deflection, rate at which current is induced is more. This is the conclusion of experiment. Relative motion, current is induced due to relative motion between the magnet and coil. Pole reversal, deflection reverses when the poles of the magnet reverse. This direction of deflection shows the direction of flow of current. Speed, faster motion of the magnet or coil causes a faster deflection, that is, rate at which the current is induced is more. Faraday's law of electromagnetic induction. This production of electric current across a conductor when exposed to a change in magnetic field is known as electromagnetic induction. Thank you. Then after the electromagnetic inductions, we are going to the mathematical derivations. The induced electric field. Faraday's law generalized the electrostatic rule del cross E equal to 0 to the time independent regime. The diverse of E is still given by Gauss's law. As you know that Gauss's law del dot E equal to 1 by epsilon 0 rho. If E is the pure Faraday field due exclusive to changing B with rho equal to 0, then del dot E equal to 0, del cross E equal to minus dou B by dou T. This is mathematically identical to magnetostatics also, as you know that del dot B equal to 0, del cross B equal to mu 0 J. Faraday induced electric fields are determined by minus dou B by dou T in exactly the same way as magnetostatic field are determined by mu 0 J. Then Biot-Savart's is E equal to minus 1 by 4 pi integral dou B by dou T divided by R square R cap dot of equal to minus 1 by 4 pi dou by dou T integral B cross R divided by R square dot of. So these are the expressions you have already discussed in your previous semesters. And if symmetry permits, that is the final expressions, Faraday's law in integral form, closed integral E dot D equal to E dot dl equal to minus dou phi divided by dou T. Then comparison of magnetostatics and electrostatics. The divergence and curl of electrostatic field is del dot equal to 1 by epsilon 0 rho. That is Gauss's law. Del cross equal to 0. Also, these are the Maxwell's equations for electrostatics. If you move to the magnetostatic field, del dot B equal to 0, del cross B equal to mu 0 J. These are the Maxwell's equation for magnetostatics. These are the two major four equations we have already studied. Also for the Maxwell equations and force law, F equal to Q into E plus V cross B. So these are the some of the conditions, some of the notes about the electromagnetic induction. Thank you for your attention.